Our first speaker today is Drew Morrill, who is graduating from the University of Colorado Boulder. His research is in physics, and he did his research advisor is an old friend of a friend of mine, who I've known actually for many years, Margaret Murnane. He completed his practicum at Lawrence Livermore National Laboratories, and he's going to be talking today about the development of mid-infrared lasers for strong X-ray high harmonic generation. So please join me in welcoming Drew to give his final presentation.
Yesterday, many of us in this room had the chance to visit the DART facility at Los Alamos, which is an absolutely remarkable facility for a number of reasons, right? You can detonate an explosive right next to the control room in a controlled manner, but more than anything, in my opinion, DART is a remarkable light source. It's a system for delivering hard X-rays over a certain amount of time with a high brightness, a high flux. I think that the history of science as an enterprise has kind of tracked our ability to probe the universe. How do we measure the world? And early on, we just used sunlight or sound or whatever. As we developed radio waves, we were able to probe astronomy. Lasers have helped us probe materials, X-ray sources, electron beams. These are the ways that we advance our understanding of the world. So I want to keep that theme in mind during this talk. We are developing light sources to enable science. So you might not see as many hypotheses or significant figures or whatnot in my talk. I'm talking about building a tool. And this tool is a light source that generates soft X-ray radiation on a tabletop scale, tables like this that could fit in a laboratory. And we do that by converting light from a tabletop laser system. So my talk is going to basically be broken up into two parts. First, I'm going to talk about how we generate this soft X-ray light. It's through a process called high harmonic generation that I'll talk about in depth. The second part of my talk, I'll be talking about the laser system that enables this high harmonic generation. But before we get there, I want to talk about what soft X-ray light is to begin with. Many of us in this room are probably more familiar with hard X-ray sources, for instance, a DART that might have MEV X-rays. To me, that is as hard as it gets, right? When I talk about soft X-rays, I'm talking about X-rays that have energies on the scale of, say, 100 eV up to 10 keV. And so for me, a 10 keV photon is a hard X-ray. And that might be funny to some of you, but in reality, there's actually a lot of interesting physics that can happen in this range, and it's actually extremely difficult to generate coherent radiation in this energy range. And just to give you guys a sense of where this lies on the scale, right? So we have visible radiation with energies on the order of 1 eV, wavelengths on the order of, say, 500 nanometers. Then you go into the extreme ultraviolet, and the soft X-ray region basically fills this region between EUV and hard X-ray. Why is soft X-ray light useful for scientists? Well, there's a number of different reasons, but the fundamentals are that this region of the spectrum has a little bit of wave-like properties, right? It's not just like a particle shooting through a material that would give you just sort of a shadowgram. You're able to actually use the diffraction of this light off of materials to study them in unique ways. The resolution of a microscope is limited by its wavelength, right? So these sort of wavelengths are on the order of a scale of a nanometer, which allows for extremely high resolution microscopy. But in addition to that, the way that we generate this allows us to have femtosecond or even attosecond time resolution if we're studying dynamic processes. An example of one of the applications that I've worked on in my PhD here, this is studying a little chunk of coral using the soft X-ray source at the Advanced Light Source in Berkeley, California. And this allowed us to basically map the crystal structure of calcium carbonate in a biologically grown sample. And this was done basically through a process called coherent diffractive imaging. You shine your soft X-ray light through some sample, it diffracts, you measure that diffraction pattern, and you reconstruct an image computationally of that object. There's, of course, other applications, biological imaging is a big one for the soft X-ray region because there's this so-called water window, right? This is where carbon is absorbing, oxygen is transparent, hydrogen is also transparent. What that means is that samples in this spectral region are water is transparent, but carbon is absorbing, which could enable, in principle, extremely high resolution biological imaging. Of course, there's other applications, for instance, studying materials under extreme conditions, looking at core level spectroscopy, warm dense matter, for instance. But at the moment, if I wanted to go do these measurements, like I did over my PhD, we would go to a facility like the Advanced Light Source in Berkeley, or here's the EU XFEL. These are facilities that many of us are familiar with. They cost billions of dollars, and they're incredibly powerful for what they are, but it would be incredibly useful for the scientific community if we had access to soft X-ray radiation in our laboratories. And that's the goal of this project, to make a tabletop source of coherent soft X-ray radiation. This is actually a picture of my lab in Boulder. It's small, much smaller than that. So how does high harmonic generation work? The principle of it is that you focus an intense, typically infrared, laser pulse into some noble gas. We often use helium. Then a process called tunnel ionization happens. Effectively, you distort the potential that these electrons feel in your noble gas to the point where the electrons will actually tunnel away from their parent ion. And this process is actually tracking the oscillating electric field of your driving laser. So this electron makes a long excursion away from its parent ion, and sometimes when the electric field changes direction, that parent ion is reaccelerated back, or the electron is reaccelerated back to its parent ion, and it recombines with a lot of energy. And the energy that it releases comes out in the form of soft X-ray radiation. So what you need is a powerful driving laser with just the right parameters focused into some sort of noble gas. It sounds simple, but it's complicated. It's difficult to do, and that's what I've been doing for my PhD. Our schemes for doing this are generally filling a glass capillary with a gas such as helium under high pressure, and you have to tune everything just right. You might ask, well, why don't you just tune up, bring the power of your laser up higher and higher? Well, you're not really forming a total plasma in this. You actually want a relatively small percentage of the atoms to be ionized into a plasma so that you can get the phase matching correct, such that you actually have a coherent buildup of this soft X-ray light. So in practice, what this looks like is something like this. This is a glass capillary with some sort of gas inlet that allows us to build up high-pressure gas. This is a piece of glass capillary that we drilled a hole out the side with a CO2 laser. So the gas actually goes in here in this tiny little 100-micron core diameter glass filament, and you focus a multi-millijoule laser pulse into that to do high harmonic generation. So high harmonic generation is a relatively simple, straightforward thing to do if you're talking about generating extreme ultraviolet light. Titanium sapphire amplifiers that operate at 800 nanometers are widespread in many laboratories across the US, but the reality of the matter is if you want to generate shorter wavelength, higher photon energy soft X-ray, you need to drive this process with a longer wavelength light. And that's simply because the cutoff energy, the maximum photon energy that you can generate, scales with the intensity of the laser roughly times the wavelength of the driving laser squared. Okay, so we are trying to generate a spectrum similar to this, a spectrum that spans the entire soft X-ray region that can be used for science applications. But to do so means that you have to drive it with mid-infrared light. The laser that I'm building operates at 3-micron wavelength. To give you guys a sense of what that is, this is a laboratory kiln. Let's say you set that to 700 degrees Celsius. Okay, it's a black body. It's emitting radiation. You feel that radiation. The peak of that radiation, that heat that you feel, is at about 3 microns. That's the type of light that we're working with. But we're converting it all the way to the soft X-ray region. So that's just sort of my introduction of how high harmonic generation is relevant and how it works. The bulk of my research is actually in developing the laser system to actually drive high harmonic generation. So I'm going to be describing that, and I recognize that many of us are not laser physicists. So I will try to cover a few different scopes, I guess, so that most people can try to get something from this. Just to generally summarize what we're trying to build with this project, we need a laser that operates in the range of 2 to 4 micron wavelengths. So this is a mid-infrared laser. That's not entirely difficult to build on its own. one of the things that's very challenging about it is that you need these pulses to be very short, on the order of 8 optical cycles. So at 3 micron, an optical cycle is about 10 femtoseconds. So these are about 80 femtosecond pulses that we need. Now, another challenge of this is that because the individual photon flux of X-rays coming out of this per pulse is relatively low, potentially on the order of 10 to the 6 photons, you need to operate this at a relatively high repetition rate. And this has advantages for doing experiments because you're able to get significant statistics or do a lot of things that are challenging to do when you operate at just a single shot or maybe multiple shots a day or something like that. So the system needs to operate at a relatively high repetition rate, and that introduces a whole host of problems with thermal management. If you can fire your laser once and then you let it cool down over the course of the next, I don't know, second or minute, or if you're NIF, several hours or days, whatever, well, that's one thing. But if it needs to fire 1,000 times a second, then you need to figure out very carefully how to deal with heat. Because these laser systems, if one part of the breadboard warms up by a fraction of a degree, the whole system goes out of alignment. The pulse energies might seem meager. They're on the order of 1 to 3 millijoules. However, it's sufficient for the purpose of high harmonic generation. Okay, so here is the diagram of our laser system, at least as it stands now. This is probably confusing to many people in the audience. I'm going to walk through it, but then I'm going to try to step back and explain it in a way that might be a little bit more understandable. But at the heart of our laser system is actually technology from the telecommunications industry. So the front end of our system is all fiber. And it starts with an erbium oscillator that operates at 1.5 microns. This is the telecommunications fiber optic wavelengths. And that's great for us because that technology is robust and very well developed. So we have an erbium oscillator that makes pulses at 1.5 micron, and we split them into 2 different erbium-doped fiber amplifiers. If you've ever worked in telecom, you might know that an EDFA is something that's found roughly every 50 kilometers in our telecommunications system as a booster for these signals as they propagate. This is a very robust technology that we've basically hijacked and customized for ourselves. We have 2 different arms of this. One of these generates 1 micron light through a highly nonlinear fiber. So we generate a dispersive wave, which shifts the wavelengths from 1.5 micron to 1 micron. And we amplify that through a ytterbium-doped fiber amplifier. This is sent into a free space, cryogenically cooled ytterbium-YAG regenerative amplifier. That's a lot of jargon, I get it. But we produce about 15 millijoule pulses at 1 micron, and that is our pump for an optical parametric amplifier. The other arm of the system also has an EDFA to amplify your light at 1.5 microns, and this is the seed of the OPA. We shape the pulses, we stretch the pulses to do chirp pulse amplification, we amplify those 1.5 micron pulses using OPA, and in the process we generate 3 micron light. This is then compressed and produces 3 micron pulses that at the moment are below the millijoule threshold, but we're currently scaling up powers. Okay, now I'm going to explain what all of that meant. Okay, so you might ask, okay, why not just take a laser, a normal laser, right? Most of us have an idea of how a laser works. You take some sort of gain medium. It's got 2 different levels, okay? You excite electrons in that gain medium. You store a bunch of energy. You send in the seed photon. It excites stimulated emission, and you have 2 photons coming out. You do it again, and you have 4 photons and 8 photons, and that's how a laser works. So why not just choose some material that has some transition that's at 3 micron? You would think that's the easiest way to do it. Well, in reality, lasers are actually quite limited by the availability of appropriate gain material. So there are chromium-doped and iron-doped chalcogenide gain materials that are promising, but that technology, in my assessment, is not really there yet. So our approach to do this is via nonlinear frequency conversion. You start with light that's cheaper by the dozen. 1 micron light. Okay, this stuff, you can buy it at the grocery store. It's got, it's very easy to produce a very large quantity of 1 micron light. Okay, this is our pump for this optical parametric amplification process. In this process, you send in an intense 1 micron pulse and you seed it with a little bit of 1.5 micron light. And a process called difference frequency generation occurs in which you generate a 3 micron pulse, which is simply defined by this pump photon energy being this, and then it splits up into 2 lower energy photons. So this is the photon that we're after here at 3 micron. Now, this sort of amplification scheme actually has a lot of benefits. A regular laser stores a bunch of energy in your crystal, in your gain medium. This is an instantaneous transfer from one wavelength to the other. It's three-wave mixing, which means that there's not significant heat load on the crystal, which means we can do it on this tiny little thing. This is an actual picture of the crystal we're using. It's a periodically pulled lithium niobate crystal. The other advantage of this is that simply by tuning the angle or by changing some of the parameters, we're able to actually amplify a variety of different bandwidths. And in a single pass on this crystal, you can have gains as high as 10,000. Optical parametric amplification is a really fascinating tool that we've been studying. So a simplified laser schematic, much easier to understand than what I just showed, is that you make this 1.5 micron light, you merge it with 1 micron light in an optical parametric amplifier, and you generate 3 micron millijoule pulses. These are then used for soft X-ray generation. Now, there's a little bit more to it than that. If we were simply to amplify these femtosecond pulses and do nothing else, you would burn the crap out of every optic in your system. Okay? So when you amplify a very short pulse to a high energy, you end up with extremely high peak intensities. And that's what's useful for high harmonic generation, but we need to do something different, so we stretch our pulses first and then recompress them so that we can store a lot of energy in this pulse and then recompress it to get extremely high peak powers, which are needed for high harmonic generation. The way this is done is using a GRISM-type stretcher, and the compressor is a standard grating compressor. The reason that these are different is simply because we're stretching the 1.5 micron pulse, and then we're compressing the 3 micron pulse. I'm going to skip the section. No, I think I have time for this, actually. So another thing that we do, a lot of what my research involves is what I would call dispersion management, right? As pulses propagate through material, they stretch or they compress. So we would like to be able to balance all of that. And we do that with a home-built pulse shaper. It's as simple as this. You send in a 1.5 micron light onto a pulse, onto a grating. Okay, this spectrally disperses it. And then we shine this spectrally dispersed spectrum onto a spatial light modulator, and we can arbitrarily apply phase onto this laser pulse, so we can actually shape the spectral phase of this so that we can compress our laser pulse all the way down to the transform limit. So here's basically an example spectrum without pulse shaping. This orange line here is the spectral phase. That is, how many radians ahead is 3,200 nanometers ahead of, say, 3,000 nanometers. If you have a large spectral phase, that means your pulse is not optimally compressed. So if you modify the spectral phase using this programmable spatial light modulator, you can drop the phase down until it's virtually flat so that you can effectively reach the transform limit even if you haven't perfectly controlled the dispersion throughout the system. Okay, so I just want to finish by talking about what I think is one of the most interesting parts of the system, which is actually the front end. So I've mentioned that we use telecommunications technology where we generate light at 1.5 micron, and then we shift it to 1 micron. So the way that that actually works is through this highly nonlinear fiber, where we send in a femtosecond pulse into this fiber that has a lot of nonlinearities, and you generate a dispersive wave at 1 micron. Here's some simulations that are showing the evolution of the spectrum coming in at 1.5 micron, and you generate a whole host of different frequencies. This is a supercontinuum, but you have this very stable wave here at 1 micron, which we then extract out. This is what this system actually looks like in practice. This is just the highly nonlinear fiber that's taped to this aluminum block. Then we take that 1 micron and we amplify it as the pump for the OPA. At the moment, our system is delivering a nearly immaculate beam profile, which is optimum for high harmonic generation. This is the spectrum here, and we have excellent stability, which is important for applications. So what's coming in the future? Well, we need to use this light to actually generate soft X-ray, but that's challenging because there's a lot of losses as you propagate through a standard capillary in the mid-infrared region. So we're having to use these engineered anti-resonant hollow core fibers, which we will actually be filling with high-pressure helium gas. The laser light propagates through there with low losses, does high harmonic generation, and the soft X-ray beam comes out the other side. It is housed in this system. This is a Zeus laser system, which is built by KM Labs, but we're modifying heavily to work at 3 micron. And the final thing that needs to happen with our laser system is a slight scaling of the energy, which we're working on right now to get our pulse energies up to the millijoule level. And that basically summarizes my talk. I just wanted to finish by acknowledging and thanking my advisors, Margaret Mernon, Henry Kaptein, Mikhail Hemmer. These are my lab mates, Dan Carlson and Will Heddle. Jilla has an extremely collaborative environment where you just walk down the hall and ask anybody anything, and I love that about the place. This work was absolutely a collaboration between NIST, Boulder, CU Physics, the people on the screen, and many more. I also wanted to finish by thanking the Krell Institute, the NNSA, the fellowship, for enabling this part of my life. And lastly, I just wanted to say that the most important part of this process for me has been to get to know the other fellows. And I just want to say that I have a lot of respect for all of you guys. And thank you for having so many honest conversations with me and as a group. And I respect that about this group. And I look forward to working with you guys in the future. Thank you very much.